In the last video, we did a pilot setup with the audio board, I2S, DMA, and so forth, and we got to the point of doing a simple audio pass-through. Now that that's done, I want to do some actual digital signal processing, starting with a simple echo. Then we'll move on to using the CMSIS FIR filter functions to create a low-pass filter. And then finally, I'll repeat what I did on the Teensy by creating a 0 and 90 degrees audio phase shift filter. And then finally, I'm going to hook that up to the Tayloe mixer that I developed before, and we should see that ability to create either an upper or lower sideband output. Okay, so in order to create the echo effect, the first thing we need to do is create an array that acts as the delay line. So here's a sort of a conceptual view of the delay line here, and the way it works is it's a ring buffer. So newer elements are here, the current element, the current sample is placed here, and it marches this way. So as new samples come in, it marches this way. So the element just to the right in the ring buffer of the current element is the oldest element, and the length of the delay line in units is, so each one of these is, each sample happens at 48 kilohertz, so the length of the delay line is the length of the echo. So if you had, for instance, a delay line with 48,000 elements in it, you'd effectively have a delay of 1 second. 24,000 elements, you'd have a delay of half a second, and so on and so forth. So you can see how the samples are injected into the delay line here. And the way the echo is created is basically the oldest element is popped off the list, and it's added to the current element and then output. If you want to create a multiple echo, what you do is you pull the oldest element off, you add it to the current element, and then you add the sum of those back together onto the delay line. So let's see that effect in action. Alright, so here's our delay line set up here, and I've got a delay line length of 20,000 elements, so the actual echo will be 20,000 divided by 48,000, so it's a bit less than half a second. And I've got a delay line for both left and right samples. And then finally, here's the current pointer into the delay line here. And that obviously moves forward as we receive new samples. So let's quickly page down to the code itself. Bear with me. All right, so here is the delay code itself. And the top part here is what we saw in the last video. So this is just pulling the samples from the audio board and putting them in source left and source right. And then the actual echo work happens down here. So you can see I'm basically taking source left and source right. I'm adding to that a delay gain, because you want the echo to fade over time, and this delay gain controls that fade, multiplied by wherever we are in the delay line. So this is basically the oldest element of the delay line, multiplied by delay gain and then added to source left. So enough talk about it. Let's actually flash that and see the effect of it. Okay, so let's just flash that using this version. Okay, wait for it to get onto the board. All right, it's onto the board now. Let me turn the speaker up. I've got to not turn it up so far that I get an echo. I get feedback. Sorry. Hello, 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 hello. So you can hear the echo, and there's a single echo there. Okay, so now let's do a simple change so that we get a repeating echo, and to do that, I basically just put onto the delay line the echoed signal itself. So I'll put RVal. Sorry, RVal. I'm doing this typing behind the camera, so please forgive me. I've also turned the AC off, so my apologies for the AC nose, but it is about 900 degrees here in the garage. So anyway, I've put delay into delay left and delay right, the LVal and RVal, which is the signal plus the echo. So we should get a repeating echo here. So let's just flash that to the board. Turn my speaker up over here. All right. Hello. This is a test. This is a test. So you can hear the repeating echo there just by simply changing that. So that's some simple digital signal processing. What we're going to move on to next is actually incorporating the CMSIS DSP libraries into the software. We'll do a low-pass filter, and then we'll do that Hilbert 0 and 90 degrees filter. Okay, so the first step in implementing the FIR filters is to derive the coefficients, or to get the coefficients. I'm not doing any derivation here. So, and I showed this program in a previous video, the Iowa Hills FIR and Hilbert filter designer. So I'll include a link to that video. I won't go into a whole pile of details here, but just kind of simply stated, I'm designing a low-pass filter here, and so I need to enter the sampling frequency, and then I put in the actual center frequency for the filter itself, which I've got as 2.4 kilohertz here. And then this little checkbox here means that I'm, well, you can't see those coefficients off at the right-hand side there. So basically outputting the coefficients on the right-hand side there. So these are the coefficients for the filter. These are the number of taps, or the number of coefficients on the actual filter. So what I've basically done is cut and paste those 160 elements into this variable here, which is my array of taps. So I've got this array here, low pass, 2 kilohertz, number of taps. So let's move back to the code and see how I use that. So this is the kind of initialization portion of using the FIR filters and the CMSIS DSP libraries. So let me get you straightened a bit there. It's a bit off. And so the first step is these filters, the FIR filters have state. So each block is related to the next block. And that's what, and this initialization portion here, in the initialization portion, you pass in this state array, which keeps track of that state from block to block. So I'm creating two FIR instances, one that handles the left channel, one that handles the right channel. And you can see here that I'm using for the coefficients for the left and the right the same low-pass filter. I do have separate state variables for the two channels though. So let's move down to where they're used, and that will be all the way down here in do phase. So this is where I'm actually using them. So it's that same piece of code up front that pulls the samples into the left and right buffers. Now I'm actually not using the right buffer here. I'm just using the left buffer. And then here's the two FIR invocations here. So this is the actual filtering here. So you pass in the instance of the filter you're using. You can see I've got a separate instance for the left and the right. And then I'm passing in source left into both invocations. And then the output appears at destination left and destination right. And then I'm simply using destination left and destination right here. So you can see I'm pulling the left channel value and the right channel value out, and then putting them into our TX buffer, which is TX buffer and RX buffer are the DMA buffers respectively. So now let's do a little quick walkthrough of the test setup here. So here's the board that you've seen before. Here's the PMOD board, and the PMOD, this time the input to the PMOD is coming from my signal generator. So just zooming into that. I've only got one channel enabled, so this is effectively the left channel. And I've got that set up to output 1 kilohertz at 800 millivolts peak to peak. And then back down to the board, here's that signal generator input right here. And then I'm pulling out the output here and I'm sending that to my scope. So just panning up to the scope, you can see the signal there on the scope. Now I've got that for both channels, but they're kind of overlapping, so you can't quite see it. So let's just shift the those two channel down. So there's the two channels down there, and so you can see they're exactly in phase as you would expect. So let's vary the frequency and see what happens as we first increase the frequency. So let's go up. I'm up at 1300 hertz at the moment. All looking good, no attenuation. You can start to see some attenuation on the signal now. So now I'm up at 2400 hertz, and there's a significant attenuation there. So that's actually the 2400 hertz, that's actually the 3 dB down point. And then going up higher and higher, now I'm up at 3 kilohertz, and you can see the significant attenuation on those signals. Higher and higher, and you can see we're now up at 3.5 kilohertz, and there's the signals all the way down to, let me have a look there, 76 millivolts from that original peak of around about 400 millivolts. So that's a low pass filter in action. What I'll move on to next is doing the same but with a high pass filter, and then we'll finally do the Hilbert 0-90 degrees filter. Okay, so let's see the derivation of that high pass filter. So I'll keep the sampling frequency the same. I'll keep the FC the same there, 2400 kilohertz. You can see the actual the filter's response here, and it has gone ahead and generated the coefficients on the right here. So what I'll do is I'll pull those coefficients into the code, and then we'll see the effect of that high pass filter. Okay, so I've pulled those high pass coefficients into the code. So let's change the low pass filter to a high pass filter. Bear with me. And then I'll flash that to the board. Okay. All right, it's flashed to the board. Let's pan over to the oscilloscope and see the effect of that now. Okay, so there we are. We're up at 2.8 kilohertz. Let's go down and see the effect. Obviously, we should see a greater attenuation as we go down in frequencies, and that's exactly what we're seeing there. So now down at 1.5 kilohertz, and the signal's at 92 millivolts peak to peak. Going back up there. Here we are up at 3 kilohertz, and the signal's 476 millivolts peak to peak. And then obviously as we go all the way up there, you can see there's no further attenuation. So you get the picture. I mean, I can continue to play around with these filters. The Iowa Hills software allows you to design notch filters, bandpass filters, all sorts of filters. So I'll give a link to the previous video that I had, as well as the Iowa Hills filter software itself. Great piece of software, a lot of fun to play around with all these different filters. So what I'm going to move on to now is kind of the final step, at least in the DSP side of things, and that's to introduce a 0-90 degree phase difference between the left and the right channel on output. So that's coming up right next. Okay, so here we are back in the Iowa Hills Filter Designer. This is a different program. This is the Iowa Hills Hilbert Filter Designer, but the setup is very similar. So for passband, you pick phase added. The sampling frequency is as before, 48 kilohertz, and then your FC and bandwidth here, and this is in terms of the Nyquist frequency, which for a 48 kilohertz sampling rate is 24 kilohertz. So I've got 0 as the center frequency, because I want to go down as far as possible down here, and then all the way up to 12 kilohertz. And then for phase add, you'll be creating two filters here, one for plus 45 degrees, one for minus 45 degrees. So this is the plus 45 degrees. You can see here this is the phase here, which is as you can see, it's actually 45 degrees, as you can see up the top there. But you can see that as you go down in frequencies, you start to get this sort of roll off here, and the phase deviates from that 45 degrees. So it's kind of not good below about, let's say, 375 hertz in this case. So you kind of have to do something about that, either filter it out or what have you. So what I'll do is I'll go away and generate the plus 45 and the minus 45 coefficients. I'll grab those coefficients, put them in the code, and then we'll come back and see the results. Okay, so we're back in the code, and we're back with the AC on. My apologies, I can't take the heat in here anymore, so my apologies for the AC noise. But we're back in the code here, and you can see I've got, for the coefficients left, plus 45 and minus 45. And then let's just pan over to the oscilloscope to see that in action there. So bear with, let me just zoom in on that output there. And as you can see, those two signals from the output are indeed 90 degrees out of phase with respect to one another. Now that's the important thing about these Hilbert phase shift filters, is it is with respect to one another. So you can't take a signal and then just use one of the sides of the filter. You have to use both sides. Now you can use plus 45, minus 45, or 90 and 0, or some other combination that gives you 90 degrees. But as you can see there, let me just go up in frequency. You can see it's consistently 90 degrees. Now I'm up at 5 kilohertz. Now what we should see as we go down in frequency is around about, bear with me, around about 300 or 400 hertz or so, that relationship begins to deteriorate between the two signals. And it's going to make a liar of me now, so bear with me. So that's down at 300 hertz there, and you can see, well, it's difficult to see, but we are actually not at 90 degrees out of phase with respect to one another. So if I just zoom in on that, let's just see that there. So let's do the rough and ready eyeballing of the frequencies here, so you can see this has a half cycle of 1, 2, 3, 4, 5, 6 and a little bit divisions, but the offset to the other signal should be half of that, right, for 90 degrees, but it's actually more than half of that. So we got 1, 2, 3, 4. So you can see those signals are no longer at 90 degrees out of phase with one another, and we're down at 160 or so hertz. So that's obviously, you know, a problem that you have to figure out in the radio, either by filtering out the frequencies, increasing the number of taps. As you increase the number of taps, that response towards 0 hertz gets better. But that's definitely something that is a problem for these for this type of radio. So let's just go back up to where we know we're getting a good filter here. Bear with. And let's do the eyeball check here again. I think that's a good way of, so let's get this centered on a reticle there. So for a half wave, it 1, 2, 3, 4, 5, 6, 7, 8. And then between this and the other one is 1, 2, 3, 4. So there's our 90 degrees relationship. So now that we've generated from a single input signal, we've generated two signals 90 degrees out of phase with one another at the correct frequency without any attenuation. Next phase is to hook this up to that Tayloe mixer that I had in one of the other videos, and let's generate some RF out of that, and let's see if we're actually outputting the correct single sideband with the other sideband attenuated. So that's coming up right next. Okay, so let's just go through the test setup we've got here, just panning down to the board. The board's all the same as usual. Just to note, and I've included this software in here, I did include the SI5351 library here. Obviously I need that for the mixing, and basically what I've got coming out of here is 0 and 90 degrees RF signal at 7.2 megahertz. So that's coming out of here. The setup here, all this setup, sorry, you can't even see that. Setup for the PMOD board is identical to before. What I've got coming in from the signal generator is a 1 kilohertz signal. Now I'm only using one channel here, so I'm not doing any 0 and 90 degrees in here. It's all happening on the board. And then I've got that hooked up to this board that you've seen before. This is the Tayloe mixer board, my apologies. And you can see here's the two signals, the 0 and 90 degrees RF signals at 7.2 megahertz coming into the board. Here's the stereo audio signal, 0 and 90 degrees offset, coming in from the PMOD board. So this stereo jack here connects to this stereo jack here on the PMOD board. And then this uses the FST3253 multiplexer and demultiplexer to basically mix those two signals together, 0 and 90 degrees RF, 0 and 90 degrees audio signal. It mixes them together, goes through the RF combiner, and then finally out here, and this is going off to my spectrum analyzer. Just a quick note before I move on to the spectrum analysis of this. If you remember from last time when I was doing the other mixes, there was a whole pile of sort of a mess on the spectrum, and I found it was related to the cheap LM358s that I was using as op amps. I changed to the LM4265 op amps, and all that mess went away. So I guess those 358s just weren't good enough for this kind of operation. But anyway, let's just pan now to the spectrum analyzer, and we can see what's what. So let me just explain again. I've got a 3 kilohertz signal coming in there, and this is the classic sort of response we expect to see. So here's the lower sideband here. Let me just go to that peak. Bear with me. So there's the left peak at 7.197 megahertz, which is what we expect. It's 3 kilohertz less than the 7.2 megahertz carrier, and that's at minus 27 dBm. And if we go to the right peak, so then there you can see the carrier, minus 67 dBm. So we've got 40 dBs of attenuation between the lower sideband and the carrier. And then if we go one further to the right, there's the upper sideband, 7.203 megahertz, and we've got over 40 dBs of attenuation there. So that is that's a really good result. And so let me just sort of demonstrate. Here's some of the sort of the power of doing digital signal processing. I can change that upper and lower sideband relationship just by simply changing the left and right channel coefficients in the software. So I'm not touching the circuit here. I'm not swapping any cables over. Just swapping the coefficients over in the code, and you should see now, when it comes back, now we've got the upper sideband, and it's got the same level of attenuation there. So as we go off to the left, minus 27, minus 68, so that's over 40 dBs of attenuation, and then finally, oops, I've gone the wrong way there. Bear with me. And now we're down to minus 74 dBm on the lower sideband. So simply by changing some of the code, I've swapped the upper and lower sideband. So let me just go back again. So I'll swap the coefficients on the left and the right side again, recompile and flash the code, and you should see that go back to the lower sideband there. And there we go. So I guess that's the completion of part 2. I had a lot of fun doing this. I mean, this is exactly kind of what I wanted to achieve here, which is doing some nuts and bolts DSP and ending up with that 0 and 90 degrees Hilbert audio filter. And you know, obviously there's a lot of places you can go from here. I do think what I want to do is and Charlie Morris did a great series on this. He built up his own FT8 radio using this kind of DSP style of approach, and that might be something I do as a follow-up. Obviously, if you have a look down to the mixer board here, I mean, this signal coming out of here is very small. It would need to go to a follow-on stage where we amplify that signal up to 4 or 5 watts. So this isn't ready to be put on the air by any stretch of the imagination, but I certainly could put a receiver on the air. So anyway, lots of things that I can go to from here. As I mentioned in the previous video, all the code that you've seen here is going to be up on the GitHub repo. So if you have any questions on the code, or if you try and replicate these experiments and run into any challenges, please let me know. Happy to try and answer any questions. I'm not an expert in this stuff by any stretch of the imagination. I just hack around with it and have fun. So anyway, that's a wrap for this video. Hope you enjoyed it, and I'll see you soon. So I couldn't resist one final thing, and that's to actually change the sideband just by hooking up a change sideband function to the user push button here. So let's just see that in action. I'll push the button, and there's the sideband changing between left and right. And obviously there's a little bit of noise as it does the sideband change there. So anyway, that's my little sideband button implemented, and I'll catch you all later.